Good afternoon, everyone. Welcome.
Hi, Dr. Gaz.
Hello. Dr. Christina Love earned her bachelor's degree in physics education from Westchester University and her MA and PhD from Temple University. She's done research at Fermi National Accelerator Lab, Gran Sasso National Lab in Italy, and the NASA Goddard Space Flight Center. Her graduate project involved the design and construction of dark matter detectors. Dr. Love had a postdoctoral appointment at the TSA laboratory in Southern New Jersey, and she is currently an associate teaching professor at Drexel. She teaches all levels of undergraduate physics courses for a diverse array of majors and has founded a science communication event called Start Talking Science. Her current research project is called Name That Neutrino, and she is about to tell us the details. Please give a warm welcome to Dr. Love.
Well, thank you for that wonderful introduction. Thank you so much for coming today as well. So today I want to talk to you about my citizen science project. It's actually called Name That Neutrino, and it's hosted on the Zooniverse website. And I have to just tell you right now, if you start Googling and trying to find it, apparently there's the website's down right now. So I just want to warn you that strangely the Zooniverse website is like going through some problems, and Galaxy Zoo is crashed and everything's not working right now. This has never happened before, so or at least when I've been. Anyway, so I just want to give you that caveat. So I work on the IceCube Neutrino Observatory, which is located at the South Pole, and so we're able to detect neutrinos and try to understand something about our universe. I want to start off by letting you know that I've had several students work on this project. Specifically, I've had a master's student and a bachelor's, like senior research student, who have done a lot of this work. And then I currently have a bachelor's senior research student working on this work as well. But the other thing I really want to point out is that, you know, these are physics students in the physics department, but I do also have many, many other students from different majors who also work in my group. And so the idea is like citizen science is a concept where we can get anyone involved. And so I try to get different kinds of students involved in the physics process, in the physics project as well. So we've got like computer science majors, but also like engineering, mechanical engineering, even biology. I have a high school student who's worked on this too. So I try to kind of welcome other students who are interested in this field to learn something about this, whether or not they go into depth and understand this at the level of a master's physics student. You know, that's probably not the case, but for sure they can have some part in the project. Okay, so I want to start off with showing you these images of a hand, and actually just kind of ask you what are these different images? What are we seeing? X-ray, we see X-ray. Yeah. What else?
MRI.
MRI.
Visible spectrum.
Visible, yeah, just visible our eyes.
And then infrared.
Infrared, exactly. And so the key here is that these different ways of looking at this object give us different information, right? So like we see the bones with an X-ray, we see you know, the temperature here with the infrared and so on. So we can do this with astronomy as well. And so you've probably seen images like this that are looking at different parts of the electromagnetic spectrum, right? So we can look at a galaxy and okay, look in the optical and our visible range, and this is what it would look like. But if we look, you know, at the X-ray, it looks completely different. Again, we're getting that different information, and then you look at the other end of the spectrum, the radio. Again, totally different things are lighting up here, right? We're getting different pieces of information. And so what we do with IceCube, I think I'm like jinxed today.
I'm sorry.
Oh, I don't know. I could just do that. No, I'm not.
That's not you. The computer does it. That's you.
It's not me. Okay, something happened. We can do this outside of the electromagnetic spectrum. So this here I'm showing you is the standard model of particle physics, which is to say kind of like the periodic table for particle physics. So it's these fundamental particles, these things that we understand a lot of the quantum mechanics that goes into here. We understand the electromagnetic forces and everything that goes into this explanation of kind of everything that we know so far, okay? It's not complete. Actually, you might notice that gravity is not listed here at all, right? So we're not totally there yet. But we can understand a lot of these kinds of particles and use them to help us, understand other things about, say, different parts of the universe. And so particularly, I just want to highlight the electron. I'm sure we're all familiar with electrons. We know about that. You might be less familiar with quarks. Quarks are the particles that make up protons and neutrons, right? And then these three down here are the ones that we tried to focus on at the IceCube Neutrino Observatory, called neutrinos. And there are three different flavors: electron neutrino, muon neutrino, and tau neutrino. So these are incredibly abundant. Okay, there's neutrinos all over right now. They actually are being produced in a lot of different ways. So the sun is producing neutrinos, but also we were talking earlier, particle accelerators produce neutrinos. But even like supermassive black holes maybe produce neutrinos, right? The Earth itself produces neutrinos. Nuclear power plants produce neutrinos. So there's so many different sources of neutrinos. But the thing is that they rarely interact. So we don't know that they're passing through our body right now. And in fact, you've maybe heard of them called the ghost particle before, which is kind of like whatever weird way to describe it, but it's the idea that there are neutrinos passing through your body right now, but you cannot feel them in the same way that you cannot really feel, when you go to the doctor and get an X-ray, right? You can't feel that. But they also are even like interacting less, right? Like they really, really rarely interact. And then neutrinos are also kind of interesting and mysterious. I write here on this slide that they have like some strange properties. They were first thought to be massless, but we've come to think that they have a mass associated with them, though we're not exactly sure what that mass is. We also have come to find out that they have this weird property where they turn into the other flavors. So they might start out as a muon neutrino and then turn into an electron neutrino at a later time. So those are called neutrino oscillations. So definitely just like a lot of very interesting kind of weird properties. But the reason why IceCube is interested in neutrinos relates back to the fact that they are abundant, and the fact that they rarely interact, and okay, also then this fact that they're mysterious. So let's imagine there's some like very dramatic astronomical event happening that's producing some, we call them messengers. Okay, so this is coming into a new field called multi-messenger astronomy, which is to say that you can detect the light, okay, like photons, different parts of the electromagnetic spectrum, right? So we can do that. That's like one messenger, is like a photon. Another messenger you've probably heard a lot about in the past decade or so, being gravitational waves, right? So we can detect gravitational waves. But neutrino astronomy is really about detecting the neutrinos that come from those kinds of events. And so the reason why neutrinos are nice to study is because you have maybe these other things are produced at the same time. Maybe this is, I don't know, a supermassive black hole, or yeah, maybe colliding neutron star, something, some sort of very extreme event happening. And maybe they produce a cosmic ray, which is a charged particle. And so cosmic rays then bend in magnetic fields. So it's hard to tell where it came from, because if it, it interacts with a magnetic field, now it's pointing in a different direction and pointing in a different direction. And so that's complicated. Gamma rays can sometimes be absorbed and not actually make it to like your detector. And so in neutrino, because it rarely interacts, if you detect it, you know that like you're the one that gets to detect it, right? It rarely interacts so often. It doesn't interact very often. And then it's going to travel in straight lines. So neutrinos are also neutral. So they're not electrically charged. So therefore they're not going to deflect in magnetic fields. So in principle, then the neutrino that you detect will come back from, come in a straight line from where it came from, right? So we can point back to these sources in principle, okay? So that's kind of the idea behind IceCube and why we're interested in looking at neutrinos. So yeah, this is built at the South Pole, which is in Antarctica. Okay, so we're looking at the bottom of the Earth here. This is Antarctica. Over here we have South America. Here's Africa. Here's Australia. Okay, get yourself kind of understanding what we're looking at. And then here, of course, is the South Pole. So penguins are out here on the coast, right? Nothing, actually, okay, people are at the South Pole and they're alive, but nothing else is living at the South Pole. So it's a little bit of a kind of a miscommunication or not a misunderstanding that people sometimes have about penguins, right? They're not at the South Pole, they're on the coast. The other thing about Antarctica is that this is a continent. There's bedrock here, okay? But on top of it is a lot of ice, okay, right? There's this glacier on top of the bedrock. And so this is the medium that we use to detect our neutrinos. The ice was already there. So it's kind of convenient because it's really clear and it's already built for us. And we just had to be able to collect the signals somehow. Okay, so that's really what IceCube does, is tries to collect the signals that really already existed in the interaction. So neutrinos come in and they actually interact with ice, with the neutron inside a water molecule. This is a colleague of mine who actually got to go to the South Pole, and this is a pole, right? There's actually a pole at the South Pole. The funny thing about the South Pole, the actual pole, is that they have to move it because you're on a glacier, and the glacier actually moves. And so every year they have this like pole moving ceremony where they physically lift the pole because they know where the geographic South Pole should be, based on like GPS and understanding the coordinates, and they can tell that they've moved, right? That it's shifted. So that's what we're working with, is the fact that this ice is where we're trying to detect our neutrino signals from. It's also really deep down far. Okay, so we measure in Eiffel Towers to let you know what's happening here. So we're about 3 Eiffel Towers tall and about 3 Eiffel Towers deep. So our sensors aren't even until down here. And the reason for that is because this is where the clearer ice was, or so we thought. We do actually have like a dust layer that we didn't know about until we started to take data. And then down here is the bedrock, right? So that's the continent down here. So our sensors are these circular things are called, we call them digital optical modules. So for short, we call them DOMs. And there's, how many are there now? Okay, so this picture says that there's 5,160 of these DOMs that we embedded into these 86 strings. I paused for a second there because we're actively, I think just like a couple weeks ago, drilling and adding more strings and adding more detectors. So I think we're only adding, I don't know how many they get. Didn't read the newsletter. I think they added 7 more strings, but I'm not sure if we're still in the process of that or not. Okay, so yeah, so to get a better idea of what's happening here, it's called the IceCube Lab. This is the building that's, on top where all of our electronics are housed. And so that's here and that's here. And so to get a sense of scale, right, that's there, right? And here's people. So this is quite massive, right? And in fact, it's a kilometer by kilometer by kilometer, a cubic kilometer of ice, which is why we call it IceCube. That is, deep down into this glacial ice. The colors you see here are those DOMs lighting up because they're able to detect light, actually. So what happens is the neutrino comes in and interacts with the ice, and then that produces other particles that go out and produce actually light, produce Cherenkov light that we then can detect. So these DOMs are just light sensors. Okay, so they're just reading out the light signal. Okay, is how many photons do we see here versus here versus here. The reason why the colors are different is because this is like artificial. This is what we add here to tell timing information. So we did it Roy G. Biv, so red happens first, what, orange, yellow, green, and then blue. Okay, it turns into blue over here. So these detectors, you know, recorded the signature of light first, the red ones, and then the blue ones last. So this is a particle that's moving this way through the detector. Particle that maybe came from some, you know, supermassive black hole, perhaps in a far location. So this is not to scale, it's not this close. But these neutrinos coming, and that we're able to then see these light signatures in the ice in Antarctica. So IceCube sees two basic events topologies, like two basic shapes. We call them cascades that kind of grow outward like a balloon, and the other one we call is a track that, you know, travels like in a straight line like a track. These signatures will be different depending upon what neutrino flavor you have. So the flavor is the electron neutrino, the muon neutrino, or the tau neutrino, and then what type of interaction. So they're coming in and they're interacting via the weak force, and then you can have different types of weak force interactions. You can have a charged interaction or a neutral interaction. But yeah, so then they produce these other secondary particles that then produce the light that we see. So I wanted to show you this kind of animation of a simulation that we have to show how a particle could be moving through, you know, this giant red arrow is supposed to be the particle coming through, and then the DOMs lighting up saying, okay, we detected some light here. The size of the bubble that is produced here is actually related to the energy. So we animate that like a larger bubble is a larger energy and a smaller bubble is less light. So that's like what a track would look like. We're just rotating this so that you can see different parts. And this is what a cascade would look like, growing outward in kind of this like spherical shape. So these DOMs are embedded in the ice. So this is an artist's renditioning of what it might look like, but this is a photograph of when this DOM was first deployed, and we would drill down into the ice. But it are like the drills only physically go far enough, and actually what we had to do was melt the ice. Okay, so the ice was melted, and then the DOM was dropped down. And then, of course, the water freezes again because it's so cold there. So we're not getting these DOMs back, right? They're frozen in the ice. This one, you know, wasn't actually deployed. It was just part of testing. So we have one of these at Drexel that we just use for like outreach events like this. And so they're about this big. Again, about 5,000 of them right now. We are this like huge collaboration of, you know, over 350 people all over the world, including about 59 institutions in 14 different countries. So this is a picture of us at a collaboration meeting in Germany last year. This is just a map of where we all are from. And so the interesting thing is that I'm talking a lot about neutrino sources. So I'm talking about, you know, being able to detect neutrinos produced by a single, you know, thing that happened, and we get those high energy neutrinos come into our detector. But there are a lot of different kinds of experiments and things that we do try to study. So we can look for dark matter based on like different flux values that we might expect in different directions as well. Cosmic rays we can also tag. There's some sensors that we have on the surface, so we can see those sensors on the surface light up, and then also the sensors deep down in the ice light up, and so we can tag a cosmic ray, and then neutrino properties. So we also do like neutrino oscillations, like maybe through the Earth as well, to trying to compare the northern hemisphere to the southern hemisphere, and all sorts of different kinds of things. Here's me, so and us. I guess we're all here, right? So here's Drexel, and that was me. Okay, so we can imagine, you know, going to a nice dark sky and seeing, maybe seeing this with our naked eye, like this band, this milky band, right? That looks kind of like a cloud, but if you know enough, you would know that that's the Milky Way. And if you were able to detect more of the light, like with the camera, you might be able to see the Milky Way looking like this, right? And so if I was to cut that band and just like rotate it, you can now imagine looking in different parts of the electromagnetic spectrum at this Milky Way. So this is our galaxy, right? So we're looking out from our place in our spiral galaxy and looking out, and that's why we have like a higher density there in the sky. So this is what it looks like for radio. This is what it looks like for radio and optical. Okay, a really good optical telescope. This is what it looks like in gamma, and just in 2023, we were able to get this picture and to say that this is what our Milky Way galaxy looks like in neutrinos. Okay, so we were able to tag the neutrinos that we were seeing coming from this particular part in the sky that corresponded to our Milky Way galaxy. So this was just recently published in Science, and you know, it was a nice result for us. Okay, so I particularly work on what's called citizen science, and I want to start with this kind of like general analogy that if we had this jar of jelly beans, and I asked you all, maybe we asked more people, because this is a room of smart people, to guess how many jelly beans are in this jar, the average, right, would be near the correct answer. And so that's a really interesting thing about our ability to kind of estimate, but also just like the human eye's ability to like recognize patterns as well. And so that's really what I'm going to get into in a minute. And so the concept isn't that like everybody knows the answer to everything, but that there's wisdom in crowds. Okay, so if you ask enough people, you're going to get like a distribution. Okay, some people are really overestimating, some people are really underestimating, but the distribution of everyone is going to be centered around the correct answer or near the correct answer. And so this idea of like asking about the wisdom of crowds and asking for like help from kind of like the general public has happened many times, especially in the past. Edmund Halley of Halley's Comet, he wanted people to measure how long it was dark during the eclipse at their location, right? So he was like, count, or however you can measure how much time of continuous of total darkness during this eclipse back in 1715. Okay, so he was like, I need help from other people. Another, I think, really interesting result of citizen science was this game. They actually like kind of gamified their citizen science that was called Fold It. And what they were able to do was come up with protein structures that like the computer programs weren't able to get to, like weren't able to randomize and produce. The humans looking at the game Fold It actually came up with completely unique things that computers weren't going to be able to come up with. So it was a really interesting kind of concept where there's some wealth in this wisdom of crowds that might not be just solved by artificial intelligence. Okay. So yeah, so this is the website where my project is housed and where a lot of projects are housed. And in fact, it's the largest web-based platform for this like people-powered research, this idea that we're calling on volunteers to help out. They have over 1 million people who log on and help out in all over the world. And they help in kind of unique ways. So I've seen projects about like bear migration, and they're like just literally photographs of like the forest, and they ask the people, do you see a bear in this picture? And so you say yes or no. My task is a little bit more complicated, as I'm going to explain. One of the most famous Zooniverse projects that you maybe have heard of is called Galaxy Zoo. And this was actually the one that started Zooniverse. That's why it's named Zooniverse. So Galaxy Zoo has like over 400,000 volunteers. It's been running for more than 17 years. And the great like science output here, we are starting to recognize, and Galaxy Zoo is known for a long time, is that there's like a lot of real information here. This isn't about, let's get people excited about science. Okay, it's about that too, but there's real science to be done. So they have, about 80 publications on Galaxy Zoo work in peer-reviewed scientific journals talking about these different classifications. So Galaxy Zoo works in galaxy morphology, trying to talk about different shapes of galaxies. which is similar to our different shapes of the signals that we see in IceCube. So that's kind of the logic that I had. So now I'm talking about Name That Neutrino. We have had our first launch, which included, okay, only about 2,000 volunteers, but we were able to get up to 171,000 classifications. We've gone through a lot of improvements, and we're now currently in what we're calling our second launch, which has a lot more data, has almost twice as much data. And we've made like a lot of improvements that I think that I'll talk a little bit about. Okay, so yeah, so it is outreach in the sense that we do want to get anyone involved. Okay, I had actually my research student, she said, oh, my mom heard you on the radio talking about this, but she was like, oh, that's not for me. And I was like, well, that's exactly what it is for you, right? That's the whole idea. The concept is that anyone should be able to log on and do this. And the idea is that it's not the end of the world if you get it wrong also, because I think people are concerned that you're gonna mess up the research or something. Each thing is shown to multiple people. And so we call that a retirement limit, or Zooniverse calls it a retirement limit. And so for my work, we've had different retirement limits from like, 15, so 15 different people are looking at the same thing, or 20 or 30, right? So you can have this kind of check to make sure that people are agreeing, right? To make sure that there's some consensus among these people, that we don't have just a bunch of like random hackers that are going on and clicking the button, right? Okay, so one thing that I found was like has been like really like rewarding is these like chat pages where we have people, who are, from, I don't know where they are, but they can be anywhere in the world, and they're actually interested, and they're actually trying and really asking good questions and coming up with like really great points that we can then work on to like, improve our citizen science instructions, but also just like help us understand the science as well. So anyone can join this, and the long-term thing is that the data that we collect is actually publishable and useful. We have translated Name That Neutrino into 7 different languages now, including English. And Japanese. I don't have Japanese. We just recently finished our Japanese translation, partly motivated by the fact that we have collaborators in these different locations, and so they wanted to use this project, for their kind of outreach event or what have you. But also, there are a lot of different Zooniverse users in other countries. So this Zooniverse translator reached out about the French translation just because they knew that there was a lot of people in France maybe that would be interested in this. And actually Zooniverse is housed, I think their main institution is in the UK as well. Okay, so we've struggled to find volunteers a little bit compared to maybe like Galaxy Zoo. And so I did a little talk on KYW on the radio. We've tried like social media kinds of things. I also go to like collaboration meetings and explain this to the collaboration so that they, first of all, actually we go to the collaboration meetings and then there's a spike in classifications. I'm like, you were all experts, you were the ones that are doing the classifications, but fine if they're bored during somebody's talk and they want to do this. But also if they then can share it with their friends and family, their local media, use it as, as a reason to reach out to the community, as a reason to be posting about it on social media and outreach. And in fact, we've gone to a couple of high schools in the area as well, and developed some like materials that like any high school teacher would be able to use, and then let their students know about it. So that's like a big thing that I'm working on currently. Okay, so I talked about tracks and cascades, but we can have our signals kind of look a little bit different. One, in that we can talk about a signal that's like not completely in our detector. So a partial or a uncontained kind of event, or a skimming event, we have a whole nother category that we want people to identify, because this is maybe not useful, but certainly not useful in like the main analyses that are going to include like full and complete events. So we want people to identify what are called skimming. Cascades are pretty straightforward, being, you know, those spherical kinds of shapes. But then for tracks, we actually have 3 different kinds of tracks based on where the track starts and stops. So we have a through-going track, means it goes just completely through our detector. You don't see a beginning or an ending, it just goes straight through. A starting track begins inside the detector and then proceeds to move, you know, outward out of the detector. And the stopping track is the opposite. It comes in and then stops inside the detector. So we want to be able to distinguish these different patterns, right, these different shapes, because it will help us do our analysis. So first of all, we have background, right? So we want to make sure that what we're detecting are neutrinos. And so cascades are always going to be producing a neutrino signal. So that's good. Starting tracks are also always going to be producing a neutrino signal. So that's also good. A through-going track or a stopping track might actually be coming from a muon that was like produced in our atmosphere from like a cosmic ray. So cosmic rays come in our atmosphere and interact and produce a bunch of background particles, right? So we want to make sure that we're not like misidentifying the things that we're looking at. Part of the motivation for using citizen science and name that neutrino is to look by eye and to kind of recognize that there's, you know, limitations to like artificial intelligence and machine learning algorithms. So we have a really great DNN, stands for deep neural network, machine learning algorithm that does a really great job in classifying our data, but we have so much data and it's so complicated that sometimes it gets it wrong, right? And so this is a good example where the DNN actually said that this was a through-going track, so a track that goes all the way through, and then the citizen users actually recognize that this is a skimming. Right, so it's a little bit hard to see in here, but there's, you know, some noise moving around, and then this signal is very much on the edge of the detector. So this should be classified as a skimming that's, you know, not giving us a lot of information, and it's not clearly going, you know, completely through our detector as you would guess a through-going track would look like. So the idea is like, can we see where are the human users and the machine learning algorithm, where are they agreeing and where are they disagreeing? And so this is the results of our first launch. And so this data specifically is for a retirement limit of 20, which means 20 different IP addresses. So actually Zooniverse also tries to tag and make sure you're not seeing the same video over and over again. We have over here a confusion matrix that's showing the user category, like what they're picking, compared to the DNN category, the machine learning algorithm down here. And so if the DNN said skimming, we see that the users said skimming about 65% of the time also. So there was some agreement there. If the DNN said cascade and the user said cascade, that was actually a 92% agreement. So that was looking really good. Then 68, and these were less, and these numbers are getting smaller too. And so you see there's some agreement and some disagreement, but then the question becomes, well, who's correct? Right, so I just said that there's some limitations to the DNN algorithm. I didn't look at all of these. There were about 4,000 videos here, so I didn't look myself. And furthermore, we found that there was some complication with our simulation and saying, well, in recognizing that there's actually no real truth value to something like this, where there are 2 signals happening at the same time. Right, so which one do you call? Is it this one or is it this one? Right, we shouldn't really be asking this question because it's not, we should be able to, you know, get rid of this data ahead of time or split it or something like that before it gets to a point where you're asking the question of which one is it, because there's two right answers, right? Because there's 2 different signals. So this was definitely a little bit of a complication for us. And so what we decided to do was look at just the disagreeing events and look by eye. Okay, so now this is our team looks by eye, our expert classification. to decide, what's really going on. So we recently published this last year to say that we see some differences here. Okay, so now I've combined, no, I'm only looking at the tracks, the through going, starting and stopping. I'm only looking at these disagreeing events up here. And so my numbers get really, really small. Okay, so there's only 20 stopping tracks, 33 starting tracks, and 121 through going tracks. But the key here, I think the really big takeaway is the fact that these are not exactly the same, right? So this is like the correct answer on the x-axis, like the expert category. And then on the left here is the DNN. So we see that the DNN is doing a pretty good job with starting and stopping tracks, but a little bit lost when it comes to through going tracks. And then the expert category is agreeing with the user category for through going tracks. So the users seem to be able to identify those through going tracks, but really struggling with the starting and the stopping tracks instead. And so fine. So we realized that there's more work to be done here because, our numbers got pretty low, but we also looked at how confident the users were in a sense of saying, like, how much did they agree with each other? So if I asked 15 people, yeah, this is 15. If I asked 15 people to look at this one video and 15 of them all agreed it was a cascade, well, I should have a 1 over here. I don't even have any of none of my videos everybody agreed with, fine. But even like 80% agreeing is not all that huge, and 60%, and we see that this is pretty kind of skewed. It's actually below. And so there's a lot of disagreements is what we recognize. And so we thought there were a couple reasons for this. One, because there are maybe these coincident events, right? So of course they're not going to agree because there's 2 different signals to look at. So that's part of the problem. But also we looked back at a lot of our instructions and the clarity of the videos and saw a bunch of different ways to improve. Okay, so we had a poll that we sent out and asked for feedback on the tutorial and then the instructions and everything. And so we've made a ton of improvements. So one thing that we did was we looked back at our Monte Carlo to understand this in more depth, because in fact, these videos that we're using right now are simulation. And so we can go back and recognize exactly what kind of particles were thrown at this detector to produce this kind of signal. And so we went back on that to make sure we understand how to get the correct answer, the truth value in a more time efficient way than just the experts looking at it themselves to make that expert category. We also found a way to reduce those coincident events. So that, hopefully that was the plan. And then we improved a lot of other things like the instructions and the workflow and all of that. A long-term picture here is to select on events that the DNN, the machine learning algorithm, knows that it's getting it wrong. And those are the kind of events that then we can ask the citizen users. Okay, we can go back and say, okay, the DNN got this wrong, but can you all agree on this? And maybe you can give me some information, some more information, right? And classify all of our events that way. We want to also, this is not where we are yet, but this is where we are moving to. And this is a really great other Zooniverse project called Gravity Spy that's looking for gravitational waves. So the LIGO collaboration has a Zooniverse project like this. They have 4 million classifications or something like that. They're way ahead of us. But the point is they have this really great structure that kind of forces people to motivates people also. You're I really want to get to that locked level, it gamifies it a little bit, but also it lets you kind of practice. And so I want to implement this sort of scenario where it's a forced tutorial and maybe give you the right answer. Are you right or wrong? So that you kind of have an idea of what's happening. So the other thing that we looked at was to compare our users and our DNN for different confidence levels of the DNN. Okay, so this is our machine learning algorithm confidence, not necessarily accuracy. So on the this is the Y. On the Y-axis, this is the accuracy. And so what this is saying is that the blue here is the machine learning. So the more confident it is, right? So it's 100%, 90%. I'm very confident that this is the one that, you know, it's a cascade. I'm 99% sure it's a cascade. It actually gets it right. It's 99% accurate up there in that scenario. But as we go down, okay, it's not exactly on this line, but as we go down, we see that for lower confidence values, the accuracy is going down. So it's like the DNN knows that it's getting wrong. He's like, this is my best guess, but I'm only 40% sure. And so what we wanted to do was see how the users are comparing. And so the orange line here is showing the users. So, okay, the DNN is actually outperforming the users at these high values, which makes sense because we know the users aren't very confident, right? They were only like 50% confident in agreement. But the DNN is quite confident, and so the users are getting outperformed by the machines, you know, down here. But when we get to these values where the DNN is less confident, the users are actually outperforming the machine learning algorithm. And so our data that we currently have running is selected only on these values where the DNN has a low confidence value, right? How can our citizen scientists be useful? Well, maybe this is the area, right, where we know that our machine learning algorithm is going to be failing, and actually maybe our users are onto something here, right? And so here's our preliminary results for our second iteration so far. This is the DNN versus the Monte Carlo truth. So now we have a value for the Monte Carlo. I don't have to look at all these videos myself. And we see that the DNN is all over the place. Like, it's not getting the correct value. And that's because it's low DNN confidence. We particularly picked the values that we knew the machine learning algorithm would be struggling with. So this, you know, is good. Like, this makes sense. It's kind of like, okay, there's some dark blue here, but, you know, kind of not a lot of diagonalization, right? So our users have been able to, it's starting to look like, outperform the DNN in some of these categories. So instead of 44%, we have 60%. Instead of 30%, we have 56%. Instead of 48, we have 62. And we see kind of a little bit more of a diagonalization. I will be the first to admit that this is not perfect over here. There's still some confusion happening. And what I've noticed also from like answering questions on like the talk pages is that the reason why the DNN is struggling with these events is because they're hard to classify. They're like low energy perhaps, or there are still coincident events. I don't know how they keep leaking in there. There's a lot of noise. Okay, so there's a lot of kinds of different things that make these particular videos a little bit extra hard to classify. And, you know, makes sense because the machine learning algorithm was struggling with these as well. The other thing that we're looking at is kind of like, what are these people doing? You know, these people who are classifying. And so this is a histogram showing on the x-axis here the seconds that it takes them to classify. To, like, when they open the video, like they open the thing and they click and it says how many, you know, how long did they stay on this page before they click to the thing? Well, the wild thing here that I didn't recognize is that there's this huge bit of people who are like, bam, this is the answer. The videos are 6 to 7 seconds long themselves. So these people are not watching the videos. So, well, first of all, maybe we do have these click hacker clickers or whatever, kids, or I don't know who's pushing the buttons. But the key here is that we can cut, right? So we can cut these people out, and we can maybe make some more instructions. Maybe they think it's an image rather than a video. They don't recognize that they have to push play. I don't know. We can look back on the instructions and kind of understand why that's happening. So we just started to look at this user level where we can look at like, yeah, how long did it take you to classify? But we can also kind of like, I don't know, like upvote the people who really seem to know what they're doing, and like downvote the people who are really regularly getting the wrong thing, right? So we can also weigh based on like IP address, or they also make an account name if they're really interested. So we're starting to look into this as well. Okay, so I just wanted to conclude here, you know, in just 2 years, really, this Name That Neutrinos Universe project that's helping the IceCube Neutrino Observatory, look at their data and understand how to classify this data, and ideally, long-term, really have the machine learning algorithm and the citizen science project work in tandem to help kind of analyze way more of our data. And then we've had, you know, over 250,000 classifications. We have now over 3,500 volunteers that are registered. So there's even more that haven't registered. And yeah, I do want to like tell you more about it, but I do believe that the website's down right now, which is just the most ridiculous thing that's ever happened during a talk to me. But if you want to save the website, you can scan the QR code here. Maybe I'll spam you later with let you know that it's working now. Thank you so much for your time. Thank you.
Questions?
Where can I find more information about the IceCube project itself?
Yeah, so
Public information about that.
Yeah, so IceCube has a really extensive kind of website and actually a really big social media presence too. That's the tutorial. So you can for sure look for, I thought I had their handles. Anyway, so yeah, if you just really, okay, first of all, don't Google just IceCube because you'll get the wrapper.
Yeah.
So you have to Google IceCube Neutrino Observatory and you will find the website. And then there's actually like a ton of social media handles that they have that are really quite active as well. So they do try to like kind of.
I just wanted to ask because, you know how search engines are nowadays, so.
Yes, no, IceCube Neutrino Observatory, not the wrapper. Yep.
The detectors themselves, you said you're just collecting light. Are those just like kilometers, single element detectors?
Yeah, so they're photomultiplier tubes that are like a little bit more enhanced,
Okay.
which is why we wanted to call them digital optical modules. I think it would sound fancier. And in fact, actually, the ones that we're currently deploying and maybe deployed a couple weeks ago, we've enhanced those as well. So they actually have more of an egg shape. So we call them D eggs instead of DOMs. Our naming conventions all over the place. But so, yeah, so it's
So
pretty much.
they're not discriminating a wavelength or wavelength regime. They're just like.
You know, that's a
You're not
great
gonna get a whole lot of
question.
background, right? You're under trial.
Yeah, and I mean, we're pretty much just getting Schrankel flight. So I think that we're actually more tuned to those wavelengths, but I don't know how much we're recording it. That's a good question.
You mentioned you're getting Cherenkov light, and so from that, is what's happening that a neutrino is interacting and causing particles to kind of fly around at the speed of light in a vacuum in a different medium, and you're getting light from that?
So what happens is, yeah, the neutrino interacts. You have most of it correct. The neutrino interacts, produces another. So for example, if it's a muon neutrino, it produces a muon.
Okay.
So the muon is flying off at a speed that's faster than the speed of light in that material.
Yeah.
So yeah, so this idea of the Cherenkov radiation is the same idea as like a sonic boom for sound and air,
Yeah.
but this is for light and material. So it's not moving. Okay, it's not even fast, but it's not moving at the speed of light in a vacuum, right? It's still less than that.
Sure.
Yep.
Okay,
Yeah.
thank
Yeah. Good question.
The cube that these videos happen in, what's the scale?
Yeah.
Very
So
small?
that's the 3 Eiffel Towers tall. So huge, actually.
Okay.
Right, but I want it. So the videos are made in the simulation. So this is like a quite complicated, like, accurate model of what's happening, but I want to put a couple Eiffel Towers here so you recognize that, yeah, this is
the
yeah,
border.
this is a cubic kilometer by cubic kilometer by cubic, the third dimension, cubic kilometer. Yeah, so huge, right, so huge. Good point.
So are you getting
light responses that are that massive from a single neutrino? Or are these groups of neutrinos?
So that like, I mean, this is a bad example, but this like signal that comes together is coming from an individual neutrino producing an individual reaction, yeah. So these are, I mean, we can see other neutrinos that are lower energy, so they're lower signals, but these like large signals that go across the entire detector here, yeah, they're, you know, the size of a small city, and they're coming from neutrinos, these like super high energy neutrinos, that are coming from, yeah, these, you know, violent, you know, things like very, very high energy kind of astronomical events.
Okay, so I
Yeah.
get the through tracks, like that makes sense to me, but what's with the starting tracks or the ending tracks? Is that just a beginning of the neutrino interacting with stuff or ending
Yeah,
interacting with
it's
stuff?
just because our, you know, the detector's here and the particles are everywhere. So it just happens to be like where the interactions are happening.
Okay.
So the starting track, that's why the starting track's so interesting to us, is because that it must have come from a neutrino interaction that just happened in our detector, like at that moment. The through going track though could be produced from a high energy muon that comes from a high energy cosmic ray in our atmosphere. So that's why we don't love the through going tracks, because they produce really a ton of light as well.
These are primarily neutrinos that have already passed through Earth first, right?
So we do both, yeah.
Okay.
So we use the Earth kind of as like a filter, exactly. So when we look to the north, you're upside down at the South Pole, so everything's a little bit confused. Anyway, when you look in the direction that goes through the Earth, you're actually able to shield, you know, from the muons that produce in the atmosphere in the north at the North Pole. You know what I mean? So when you get, so you're more confident that you're getting neutrino signals when you're looking in that direction. However, when you look to the southern sky, you know, when you look up from from the South Pole, there's, you know, muons being produced in the atmosphere right there. So those are definitely, there's way more noise background in that direction. Yep.
Do you have any thoughts on why it seems like people are less likely to categorize things as starting and stopping?
That's a really great question. And I think part of it is the understanding the edges of the detector, like where it actually is. And so I'm interested in maybe trying to like make these planes like shaded in some region or in some way. Also the top and the bottom, right? I think that that's not super obvious, but also I think some of these are hard to classify and they're near the edge of the detector. And so I've seen a couple of them, like people on the top forum pages are like, hey, what do you think this is? And I have to like stare at it for like 5 minutes. And I'm like, I don't actually know, because is it starting here or is it starting here? Like it's hard to kind of tell. And again, that's why like these are the ones that are harder to classify. So I think that's part of the problem. It's a good question.
2D space, it's gonna be something lost in translation.
So I need 3D glasses. Is that what you're telling me?
Is there any mechanism to make the videos interactive in a fashion that would allow the user to reorient them?
That's what we want to do. Yeah, like
Pause.
click and like
Spin.
rotate it. Yeah, that's kind of the dream. I don't know if Zooniverse has the capability of doing that, because actually most Zooniverse projects are images as it is. So we might have to then have like it exists at a different site. And so, yeah, so it's more complicated than just like launching a new Zooniverse project. So we are talking to them about that, because I think that would be really much more clear to be able to see. And we don't even rotate through the full 360 degrees, because we also are limited for each video has to be under 1 megabyte. Which is why you see the videos aren't like super sharp
Yeah.
either. So that's a whole nother thing that we're looking into as well.
You've effectively got 4-dimensional data that
Yeah.
you're trying to get people to see in 2 dimensions.
Yeah.
Good luck.
Yeah.
So you have the, so you're collecting data from the Milky Way galaxy, or the image that you're looking at. Is there a way to, obviously you can't really move the probes or the DOMs anymore, so how are you, I guess, comparing all the data together in a span of a year?
Yeah, no, so there's a couple different things happening. So the Milky Way result actually isn't related to the citizen science result. That was using machine learning algorithm. And what you can do is you can tell the direction that the neutrino is coming based on like the direction you see of like the track, right? So you can say the neutrino, and now you know where the Milky Way is in the sky, right? So now you can point that back. Actually, the interesting thing about the science publication about the Milky Way discovery was it had to do with us being able to use machine learning algorithms to get a direction from a cascade as well. And so that you can't tell by eye, right? Because it just blows up this way. But when you look really carefully and statistically over like 13 years of data, we were able to then, confidently say that, these neutrinos are coming from that Milky Way direction, right? And tag it together. Good question.
Yeah, you mentioned there was a layer of dust near the top of the detector.
Yeah.
What is that from?
Just when the glacier was forming, right? So it happens over millions of, I don't know. Oh, this is a good question, right? Is there some like real reason? I don't know when that was formed. I don't know anything about glaciology. That's a good
How
question.
deep is it?
So it's in the detector itself. I'm sure. So there's also people who do
I'm
study
wondering if that's-
glaciology in IceCube as well. So we have published papers about this. I don't know
I'm
why,
wondering
I
if it
don't
might
know
be the KPG of that.
anything of why we okay, yes, we can look at this scale here. So there's the lab. So this is where the experiment begins. And then we go down, sorry. And so this is, so this is where our light sensors are. So we have no light sensors here. The dust layer is about like here. So 2,000 meters. Yeah, I don't know. I don't know if we know. That's a good question.
So in the videos that you're showing, they have a certain time frame. I'm guessing that's not real time.
Correct.
They've been slowed down.
Yeah, like significantly.
By how much?
Oh my gosh, so much. So
Like how many, and that as follow-up question. So, in a given day, let's say, how many of these events are detected by IceCube?
yeah, so many. Let me find the numbers. I think
Speed of light. I think it's like 1.7.
oh no, I don't have that video. Okay, so I think our trigger is 3,000 hertz. So we get 3,000 events per second.
Oh,
So there's so much reduction. That's the other. So I have a nice slide about that, about like reduction. So our analysis level is okay. We've been taking data for 13 years, but we get rid of like, I don't know, 90% of our data, right? And it gets reduced down to things that are very clear and that we're very confident about, and we can point to different directions and have these high energies and whatnot. And in fact, those like extremely high energy astrophysical neutrinos are detected more at like 10 or 20 per year. So we're just swamped with background and these lower energy kind of events that we need to be able to distinguish between. Yeah.
How are you synchronizing the timings between the optical sensors? It's like 3,000 hertz. That's a lot of information.
Yeah. No, I don't know. That's a great question. And the unfortunate thing, okay, we're installing more strings now, but the idea is that like, this was built 13 years ago. So you actually have to then think about like what the technology was 13 years ago. Of course, we can update our electronics on the surface, right? But then the cables, like what you have for the digital optical models are there. And there's stuff. Yeah.
Does the angle the particles moving make a difference? So it's measuring particles that come straight down the hole, right? But if they go through the earth, I guess, does it matter which way they're going? Or, because you said they go through everything. There's like no impact on them going through
the earth?
anything, yeah.
No, so if a neutrino interacts in the earth before it gets to our detector, we're not going to detect it. So we don't have to worry about
So the
that.
ones that go straight down the hole perfectly, or did it?
No, in all directions. Yeah, so we have neutrinos that'll come like from the side of the earth, and not cut through the whole earth, but just part of it. And so there's some limit then to where we're getting our muons coming in and slicing through some of the earth, maybe surviving and still coming to our detector.
The boreholes don't have anything to do with.
Okay, that's what I was trying to, okay. They're not
That's,
important.
right, that's just,
It's just a
That's
different
right.
layer.
Those are transient and become.
yeah.
Is there a difference in the material properties of the new ice versus the old ice?
I don't think so, because we're just like barely expanding the detector now. There's a much bigger project for the next like 10, 20 years, although who knows if that's gonna get funded at this point. That's called IceCube Gen 2. And that kind of, I think that effectively doubles the size, like in all directions. So there were some studies to see like, well, which way do we want to go? Do we just want to go this direction compared to this direction? But the drilling that we just did, weeks ago is just right next to the other ones. Because you still want it to be in your array, right? So you want them to be detected. And so you have, a limited location where that could be.
Would you be okay with sharing your email address if people have further follow-ups?
Yeah, sure. Yeah, I'm just love@drexel.edu, so that's super easy. I promise that's me. It's not some weird spam. And I'm happy to answer questions after if people have more questions.
Okay, so let's thank our speaker.